Okay, so for this set, we're going to be looking at mathematical induction, and the whole idea with mathematical induction is, it's easiest to explain using the analogy of a ladder. So let's actually just draw that ladder in. So we have a ladder, we have this process, and the whole idea is, if you're sitting at like this point in the ladder, like sitting over there, to get to that point, you would have had to step up from it. And this is what induction uses. It uses like the situation of, if you're at one step and you can get to the next step, then all the steps below that technically existed, kind of a situation. There are two types of mathematical induction, and the whole idea between them actually just differs due to the hypothesis that you use. And when I talk about hypothesis, I mean like, you know, like in the indirect proofs, you assume something and then you show that there's a contradiction. That assumption was kind of your hypothesis situation. So that is what we're going to be looking at and the differences between the two of them. So let's first just write down weak and strong and discuss the differences between them. But in applied math in first year, we generally use the strong case. But in pure maths, you'll go through the entire process, the exact, the whys, the hows, everything in between. Okay, so the first step between any of your weak or strong cases is that you prove that the first step exists, or you show that the first step exists. In other words, that's what we refer to as our base case. And the whole idea behind that is we have something and we assume that that one is true. Now, your base case does not have to necessarily be like the first piece. It could be the second or third piece when you're looking at maths, but the whole idea is you starting to build that ladder and you assuming that that first step in the ladder is true. So both of them, you have to show that and you have to prove it. Okay, so then for weak, what you're actually showing, what you need to show, is you need to show that if you have a pk, you can get to pk plus 1. So in other words, if you're on this step here, you can get to that step over there. And then once you do that, if you can show that that is true, it exists for all natural numbers. Because then you can go from pk plus 1 to pk plus 2 situation by just changing what your k was. Okay, so let's just write that down. We have the situation then, if we can show that pk goes to pk plus 1, that is true. So a tends to b, where a is pk and b is pk plus 1. Then p2 must be true because, and that is true, I know my writing sucks, we have P1 is true, and therefore P2 is true. So we had that base case situation of P1 is true. We are going to, well, we show that if you have PK, A tends to B, or A implies B essentially. So if PK is true, then PK plus 1 is true. We show that. Then anything, when we start discussing this, we have the situation of P2 must be true because we've already shown that P1 is true. Then we have, oh, well, P2 is now true. So P2 tends to P3, or actually implies that P3 is true. So P2 then implies P3 is true, and so on. And that's how we get that it is true for all natural numbers. And then true, and again, my handwriting sucks, that is actually true for all natural numbers. And I use the n with the 0, so it's true usually in a case of like 0 to 1 kind of a situation. But obviously it depends on your base case. So it depends on, if your base case starts at 2, it would be true from everything from 2 onwards. If it starts at 1, it would be true from everything from 1 onwards. So just be careful when we talk about this for all natural numbers. There is some limits in regards to that, particularly in the case of what your base case is. Okay, now we're coming to the one that we actually use in applied maths. And we have the situation, again, we prove the base case, that first step of the ladder. It doesn't necessarily have to be the number 1, it could be the number 2, depending on what kind of graphs or stuff you do, or what your actual problem is. But don't stress about that at the moment. You prove that that first step of the ladder is true, and then you're going to be looking at the case of, if you can find like a PR is true, where R is between like 1 and n, then you can show that Pn is going to be true. And then you have that situation of, well, now any n, you can just move the n situation. Then any of those n's will be true. So that the whole idea behind it is you have PR tends to Pn. So instead of pk to pk plus 1, you're going to show that you have an R value. The R is between the numbers but not including n, but it just stops before n. Then you show that Pn is true. Okay, so let's just write down everything that I said. So you have basically if PR is true for 1 to n with not including n, then Pn is true. So you're going to try and prove Pn using essentially your PR information. And if you can show that, then it's true for all natural numbers. And the same restrictions apply there. So obviously, like if you didn't start at 1 and you started at 2, it would apply for everything from 2 onwards. Okay, so in other words, you show that PR to Pn for R between 1 and n, and then the whole idea is you have all the steps that you have stepped on, including the current one. And the one before, you actually looking at the step that you're currently stepping on. So for weak, you look at the step that you're currently stepping on, and for strong, you look at all the steps that you stepped on to get there, basically, and the current one. Okay, so here we're going to discuss the template for how you approach the mathematical induction. And it's essentially recapping what I just actually spoke about, but now it's just putting it in very like step by step, what are you going to do? So when you're proving by mathematical induction, you first prove the base case. So you prove the most basic case available to you. So it doesn't have to be like number 1, but it's whichever is the most basic case that's available. So you prove the most basic case. Then next up, you make your assumption or your induction hypothesis. So if you are looking at weak, you would assume that, you know, your statement holds for some k, that value, that the step that you're on. And if you're looking at strong, you're assuming that it's going to hold for all but from your base case, essentially, to just before your kth step. Okay, so let's just write that down. So we assume the statement holds for the kth, or for some k, or for strong induction, you assume it holds from 1 to just before that k. And previously we spoke about it as R, just so that you didn't get too confused, kind of a situation between the two of them. So for all numbers less than or equal to k, assume the statement is true for all numbers less than k. Then you prove that the statement holds to the next step based on the induction hypothesis. So that's the inductive step. You prove that the statement holds to the next step based on the induction hypothesis. So less than or equal to k there, I forgot that. Okay, so again, I'm just going to repeat this. It's not necessary. You can always skip through this if you kind of get what I'm talking about. But you prove your base case, which is the most basic case. Then you have your induction hypothesis, which changes depending on whether you're using weak or strong. If you're using weak, you're basically going to assume that it holds for some k, and then you're going to prove that the statement holds for the k plus 1 step. For strong, you assume that the statement is true for all numbers less than or equal to k, and then you prove it works for the next step. So in this case, the k plus 1 step is that R value. Okay, so let's go ahead and actually get to a proof and play around with it. Okay, so we're going to look at the theorem of if T is a tree of order n, then the size of the tree is n minus 1, and you're going to use mathematical induction for it. So the whole idea with mathematical induction, if you have something that's like n, and your result is featuring the n, that's generally when you'd use mathematical induction, just by the way. So let's write down the theorem. Theorem, if T is a tree of order n, then the size of the tree is n minus 1. Okay, so yet again, we're going to use mathematical induction, and we're going to use strong induction. So when we're speaking about this, we're going to prove it using the base case. So we're going to have a tree of order 1 and show that its size is 0. So we're going to prove the base case. Tree of order 1, size 0. Then we're going to have the induction hypothesis, and we're going to prove basically that Pn has a size n minus 1. So we're going to prove that the tree of order n has size n minus 1. So when we're looking at this, and remember I spoke earlier, I had the whole p brackets 1. This is p1, and it kind of matches because you have this order 1 here. So there we go. And then you are referring to this one as p, n, and again, the matchy things you can see, n and order n. So the induction hypothesis in this case is let PR be true for all 1 to R to N. Okay, so here we have the case of it is your base case that pretty much comes in there. And then you have the one that you want to prove. And this one is not included in this situation. So just be aware of that. Because now what you're going to do is you're going to prove your PR. Well, no, sorry. Words are slightly wrong. You're going to let PR be true, and then you're going to prove the PN using your R is true. Okay, so let's go through this. We begin our proof. And we start off with the base case. So we let T be a tree of order n, T be a tree, and it's the base case of order 1. And we know there is only one tree of order 1, which happens to be the complete graph. Okay? So there is only one tree. Of order 1. And it happens to be the complete graph, which is K1. Now you know what a complete graph size is. So here you're utilizing the tree, you're finding something that you already know the size of that one, and you're going to use it to prove that, you know, it matches up with the situation. So you know that K1 has size 0, and therefore you have proved your first case, your base case. So again, with this base case, we say let T be a tree of order 1, and then we go from a tree of order 1 to prove that its size is 0. And we just do this by knowing that the tree of order 1 is actually the complete graph with one vertex, and we know the size of a complete graph with one vertex. So we utilize that, we get the results. So we've taken A to prove B, just a direct proof. Okay, so now we're going to focus on the inductive step. So to focus on the inductive step, we use our inductive hypothesis. So remember, our inductive hypothesis was a case of we let PR be true for 1 to R, and R is just below N. So we're going to utilize this. So what that is saying is that for any tree with the number of vertices less than N there, we have that the size is R minus 1. So let's actually just write that. So we have a tree of order R, the size is R minus 1. Okay, I just want to rewrite that because that E came up weirdly. So you have that, that is our assumption. That was our inductive hypothesis, we have that is true. Then we're going to utilize this to show that a tree of order N has a size n minus 1. So now we're going to say let's consider a tree. Let's use the word consider so it matches your notes. consider a tree of order n. Now we need to figure out a way to make this, the order n tree, be built up of our smaller ones, because inductive hypothesis. Can we break it up so it is built up by that? And we can, based on the things we've learned in week 2 and 3 and 4 and so on, because if we remove an edge from a tree, so let's just draw a random example of a tree, and we know it doesn't have any cycles. So a tree doesn't have any cycles. So if you remove an edge from it, it disconnects it. And the moment you disconnect a graph, you have components, right? But now because it's a tree, it has no other cycles. So the components of a disconnected tree, if you remove an edge to it, the components are going to be trees. So we can utilize that. So we're saying, okay, removing an edge, then you know here you have a T1 and you have this as a T2 situation. And both of these, I don't want to use it like that. So you have two different trees there. Let's do that to make it clearer. Now this tree is made out of vertices, 3 vertices, so we call it T3 for example. And this tree here is made out of 2 vertices. Let's just call it T2. You know, we're keeping this simple and easy kind of situation. But if we had said that our n was 1, 2, 3, 4, 5, our 5 is the one we need to prove. But we've said that everything up to 4 is correct in a way, and it has a size of 4 minus 1, which is 3. So both of these are actually less than 5. So we know their sizes. So we know this has a size of 2, and we know that this one has a size of 1. So we can utilize that to build back up to the original tree, the one where the edge wasn't removed. And that is basically by saying, hey, we know this one's size, we know that one's size, and we know sizes are the number of edges. So we removed an edge, so we should just be able to add an edge in, a +1 situation. And then if we can show that that is actually just equal to n minus 1, we have proven our case. So that's what we're going to go ahead and do. So we say, consider a tree of order n, we let e be an edge, we let it equal to x and y, which are any 2 vertices in our vertices set, where we have this as an element of our edge set of the original tree. Then we're going to look at t minus that edge. So we know that t minus that edge gives us 2 trees, because the moment you disconnect it, so we took that away, we had 2 trees. We're just going to call these trees T1 and T2, just keeping it simple. So here I spoke about them, you know, as T to the N, well not N, but T to the K situation. But here we're just going to refer to those trees as T1 and T2. You know we can relabel things as we choose. So T minus E will disconnect the graph, so it will disconnect T, giving us 2 subgraphs, and those subgraphs are trees. So disconnect T into 2 trees. And we're going to just call them T1 and T2. But what we're going to do is, obviously when we remove E, and say E was between X and Y, so that was E, X will be in one of those trees, and Y will be in one of the other trees. So that's what we say. With X is the element of T1, and Y is the element of T2. Then we're going to build up the size of the original tree based on the smaller trees, the subgraphs. So then the size of T is equal to the size of your one tree plus the size of your other tree plus the edge that you removed. Now you have to think about, because remember you need to connect this with the order. So now you actually have to tell the user, hey, what are the orders? So we're just going to say, okay, let the order of T1 be equal to A, and let the order of T2 be equal to B. So we're just leaving that at the moment. And now remember, the order of well, A has to be less than n because you're doing the whole component situation. And even if you took a tree, for example, like this, where we have 1, 2, 3, 4, and even if we remove that edge, this component will not have that. So it won't consist of the same number of vertices as the original graph. So we can actually write that in as well. So we say, okay, we know that the order of T1 is equal to A, which is less than N, and we know also that the order of T2 is equal to B, which is less than N. But because they are both less than N, they fit into our hypothesis where we have R is less than N but greater than or equal to 1, which means we can say the size of T1 is equal to A minus 1 and the size of T2 is equal to B minus 1. So now we can actually say that the size of T is equal to A minus 1 plus B minus 1 plus 1, which is equal to A plus B minus 1. And then you have the situation of A plus B is equal to N. Why is that? Because again, when you're removing an edge from your graph, you don't change the order of the graph itself. So remember that from the work that we did previously. So we can actually say that. We can go ahead and say, hey, A plus B is equal to N. So now we've proven that the size of T is equal to N minus 1. So we go ahead and say that. We say N minus 1. And this proves that Pn is true. So the whole idea behind, well, strong mathematical induction is you assume that everything below n is true, and then you basically try and build n up in pieces of smaller pieces. And then you show that it is true, and if you can show that that one is true, then it's going to be true for all n. And that's it, you're done.